Talvez eu pode colocar aqui atrás, que assim eu consigo colocar a mão. Sim, obrigado. Olha, oi, oi, oi. So I removed the introductory part because I thought there were going to be people here from last week. But anyway, anyway, so we'll. But anyway, it's good because I think I will need less than 45 minutes. No, so I will go relax and slowly. I'm a bit tired also. So this is a work in collaboration with Juan Carrasquilla, who's now all these three. So Roger Melko is machine learning group leader in Perimeter Institute, and then there's Giacomo, who finished his PhD with him, and I think is moving to Flatirons in New York. And then there's Juan Carrasquilla, who's now in Vector Institute in Toronto, right? Huh? So technically, he's a condensed matter group, but I think so. These people have moved from Monte Carlo and quantum Monte Carlo slowly to machine learning thing, and now essentially they do lots of things with machine learning. Yeah, yeah. There will even be a machine learning initiative next year with Perimeter Institute, and they're getting some more money. Yeah. Well, well. Uh, yeah, yeah. Uh, mm, mm. Yeah. The real magician. Yeah, okay. Yeah. Okay, so this is not going to be about quantum supremacy. This is going to be on improvements of on state reconstruction techniques based on neural networks, but actually not really connected to quantum supremacy. So I don't have the motivating slides and the introductory part. So for those who were here last week, if any, so the first part of the talk last week was about so it's about benchmarking many-body quantum technologies, and in particular preparations of many-body quantum states, right? And so I spent a couple of years already working on a different type of tool for benchmarking many-body quantum technologies, which has to do with kind of doing measurements that allow you to come up with a lower bound to the fidelity with respect to the target state that you want to prepare, right? And so here, essentially what I was doing over the last few years was always to avoid state reconstructions. I was only interested in getting a lower bound to the fidelity with respect to a given known target state. And now here, with this thing that I'm going to show today, I come back to state tomography, to our old friend. But of course, so the idea is that we want to simplify state description, and so in a sense, this is similar to what we may hear about from MPS tomography. But the thing is that now here I want to use a different ansatz for the states I want to reconstruct, right? And so the idea, so I think that I didn't get to show this slide last week, but so that we speak the same, so that we're on the same page. So, okay, so we know that if you have a classical system, say that you have an n-bit classical system, then this is described by, and if it's a deterministic state, then this is described by n binary parameters, right? So I mean, I need n parameters to specify the state, and of course we know that an n-qubit state has exponentially many complex parameters. And so there's this thing that somehow, I think this is connected even with the discussion we had last night, because last week I said something about the number of atoms in the universe, and then people asked me if I was Buddhist because of saying that. I don't know why, but anyway. But so the thing is that, I mean, if you count, so if you go to Google and look at the estimations by cosmologies of the number of atoms, estimated number of atoms in the observable known universe, then you will find that this number, which is more or less equal to 2 to the 272. So this means that if you look at the qubit state of, so if you have a 272 qubit state, it contains more parameters than atoms in the universe. Huh? So that's you get to this shocking conclusion, and it's a bit too much, really. But that's life. It's exponentially complex. But anyway, so the idea. Nice. Okay, I will include that in my next presentation. Okay. Yeah. I see. Okay. Okay. Good. Thanks. Yeah. 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 And so I think I got to this point last week. So the thing is that we know that physical systems typically occupy. So we know that in fact, so the idea is that actually physical systems typically occupy a teeny mini region of Hilbert space, and people have put that in formal terms. And so when I say physical, I refer to states that can be prepared by, let's say, a quantum computer with a polynomial number of gates, or by some local interaction Hamiltonian in polytime, right? And so the thing is that, so these people, so I mean, I really like these papers because they pose this question. So, okay, so if we want to represent many body physical states, is it really Hilbert space, the best representation that we should use? Or we should look for something a little bit more restricted? And so following this spirit, there's been a couple of ansatz that simplify the many body problem. And so, of course, there are many, right? I mean, I don't know. Here you can assume, if you assume that your state is Gaussian, then of course it admits an efficient description. If you assume that it's an MPS or some tree tensor network, it's also efficient. And then you can look at different symmetries. I mean, there are different ways in which we can simplify this complex problem to try to look at different regions of this part of Hilbert space that corresponds to physical states. And so the one I want to look at today is this neural networks as a variational ansatz for quantum states. And so this comes motivated by the fact that, you know, there's this big data and machine learning community that also find the same many body problem, and that they've had lots of success with these neural networks. Of course, the bad thing here is that we cannot, typically we cannot prove results that upper bounds the sample complexity of the estimations and such things. You know, it's just like here. So the spirit that I'm following is, okay, well, neural networks have proven to be very efficient for certain tasks in the big data community. So why not apply them as tool for quantum state characterization, right? And so okay, so I will. This is more or less all the slides that I'm going to show. So I will say a few words about unsupervised learning with neural networks. Then I will mention previous results on using these neural network ansatz for tomography, in particular for restricted Boltzmann machines. It's a type of neural networks that has many nice properties. And then I will go to the new scheme that we propose, right? So here this was restricted to pure state essentially, and this is something very bad because you don't want to assume that the state you will reconstruct is pure. And here, so we wanna relax that assumption and go to more general case, right? So as nice things, this one of the nice things that this scheme has is that it gives you a certificate of the reconstruction, an approximate certificate, but that doesn't need the assumption of purity or any other assumption on the state. And also, in many cases, it can handle efficiently, so you can estimate efficiently the expectation value of local observables without using the density matrix, just by combining with ideas from Monte Carlo sampling. So okay, so let me start. Neural network pure states. Okay, so there have been some papers that propose to parameterize the coefficients of a pure state with a specific type of neural networks that's very popular, which is called restricted Boltzmann machine. And so essentially a restricted Boltzmann machine is nothing but a generative model for generating, for modeling a probability distribution, right? So say that, so this is a two-layer restricted Boltzmann machine. The word restricted comes from the fact because the fact that there's no interactions, intralayer interactions. There's only interactions between the visible and the hidden units. And so essentially what you look at is at a classical, let's say, Hamiltonian. You see that, so here you have like biases. So W is a matrix that contains the weights. It's as if you had a Hamiltonian that penalizes. It's an energetic model, right? So I mean, W is some sort of interaction between, W11 is the interaction between visible unit 1 and hidden unit 1. And so we have, you know, like a matrix of these W weights. And then there we have local weights at the level of each visible and each hidden unit that I call A and B, right? So these are all vectors. And so this is, you know, this is essentially the Boltzmann distribution according to this energetic model. And you trace, so you sum out all the hidden, over the hidden units, and you get a probability distribution over the visible ones. And this is a parametrization for a probability distributions of n bits, right? And then, I mean, these things can be complex. Actually, in the general case, even assuming, even assuming that the number of hidden units scales linearly or not too far away from linearly with the visible units, you can show that sampling from this, in the general case, sampling from these distributions can be hard. But anyway, in practice, they happen to be very successful. So people have been applying them in practice to learn. So the idea is that, I mean, this is a fact that, you know, I mean, those hardness results are of course worst case hardness results. And so the idea is that, I mean, the evidence that we have is that, so this type of neural networks have been, in practice, very successful at learning unknown probability distributions from samples, right? So essentially, you give, so you generate samples, strings of zeros and ones, and then you try to optimize the values of these parameters such that you get a probability distribution that samples so closely as possible from the unknown probability distribution that generated the experimental data, okay? And so this is my 1-minute introduction to this type of neural networks. This, anyway, in our case, we'll be interested not only in these restricted Boltzmann machines, but actually any neural network model, probabilistic neural network model for unsupervised learning. And so I said that, okay, so that was classical, and then there were these papers, and there are many more. But in these papers, what they do essentially is they propose to take these neural network ansatz, and in particular these restricted Boltzmann machine ansatz, for the probability amplitudes for the coefficients of a quantum state in a given computational basis, right? And this is what people have called neural network quantum states. Okay, and this is an ansatz, and they have many properties, and people have studied, in particular in this last paper, they study very formally the connection between MPS and MPS states and neural network states. So I think that these are nice papers to read. Sorry? Well, so that's the problem. I mean, that was my motivation. That was my critic to them, and so the idea, what I'm going to show today is a solution to that. Yeah, yeah. So okay. So like you say, okay. So these people came up, of course. So this was just a proposal of the ansatz, if you want, as a variational ansatz for optimizations, for instance. But of course, once you have that, you can also use it for state reconstructions, right? So I'm not going to describe these papers in detail. So here in the first version, they really assume that you have a pure state, and somehow, so this visible layer here, essentially what you input to it is the outputs of the measurement on some computational basis. But of course, you have to vary the basis, so you just can't measure in a single fixed basis because you don't have any phase information. So in the simplest case, what they did first was just assume that you have a quantum state that is pure and with positive real coefficients in a given fixed basis. So then, of course, there is a one-to-one mapping between the probability amplitudes and the probabilities, right? But of course, that's too much a simplification, and you don't want to assume that. And they have some tricks to go into other bases and capturing some phase information. But of course, this doesn't work in general. In the end, what you need is some a priori information of the state that you want to reconstruct, right? So and then they make an extension to the mixed state case, which actually in the end is just simply they propose the same ansatz to the purification of the states. I mean, in the end, they're using the same trick. They're essentially assuming that the pure states that the states to reconstruct are pure, and you know, it's not reliable because it's. I mean, as I said, you need to have some prior information of the state, or you make assumptions, or you don't have a clue of really what's the performance of your reconstruction, how close it is, right? And so these people were given a mini course last year in Sao Paulo, and then I said to Roger, no, but come on, you're assuming that the state you want to reconstruct is pure. This is not what we want to do in quantum information, right? So I mean, the idea now, so this is a proposal to fix for that problem, okay? And then of course, well, so in their case, they work only for restricted Boltzmann machines, and I'm going to show you something that is versatile in the sense that it can adapt to any type of probabilistic neural network model, okay? So those are my motivations if you want to. And so what they did was to sort of parameterize the coefficients of a pure state with a neural network ansatz. And so here what I'm going to do is I'm going to parameterize the measurement outcome probabilities with a neural network ansatz. And we will see that that will allow me to go to the mixed state case and some other advantages, okay? And so, all right, so our idea is instead of parameterizing probability amplitudes with a neural network ansatz, we will directly parameterize the measurement probabilities with the neural network ansatz, all right? And of course, if I'm gonna be looking just at the measurement probabilities, at the probability distributions of measurement outcomes of a state, and I don't want to lose any information of the state, I have to consider informationally complete measurements, all right? So if you have if we consider an informationally complete measurements, then all the information of the quantum state is encoded in a, well, I mean, I think this word is wrong. I shouldn't say classical probability distribution. It's just a probability distribution, right? I mean, in a vector of real numbers, right? And so as advantages, so as I said, this is unconditional, and I am abusing a little bit language here when I say unconditional. Unconditional means that I don't need to assume absolutely anything about the state to reconstruct, but the certificate or benchmark that I will get is approximate. I mean, if I wouldn't assume anything of the state to reconstruct and my technique was efficient and plus I had a certificate, then I solved the certification problem for general states, and I'm not claiming that I'm doing that, okay? So we pay a price, right? I mean, we will see that instead of having a lower bound to the quantum fidelity, we will have another benchmark, which in a sense is a bit dirtier, but it's more practical. Or it can be more practical. So that's the spirit of the, and so it can work with any neural network model, not only restricted Boltzmann machines. And one nice thing I insist is this thing that somehow we will be able to estimate the expectation values of some observables, in particular local observables, using Monte Carlo sampling directly from the reconstructed probability distribution by passing the quantum state. We never write down a state vector or a density matrix, okay? And so there's this nice figure here. So as David can see, perhaps, so last week I didn't have the neural network here, so I hope this clarifies a little bit what I wanted to show last week. Yeah. No, in principle, no. I should think about it, but let me show you the answer. Let me show you the answers in detail, and perhaps you will see what I mean. Okay. So now I have this. So I mean, you should think of this. So you should think of this box as some so I mean, I was talking about the restricted Boltzmann machines because they are able to generate samples according to this Boltzmann distribution, but any neural network that has some probabilistic model to generate samples could do the job. You could simply think that here you have a black box that generates samples, strings of zeros and ones, and then now you, oh, no, oh, okay, wait. And now you simply contract it with some local tensors that I will describe. Okay, let me show you. It's the next slide. And so, so let's first start with a generic density matrix. Let's forget about neural networks. Okay, so now I consider a generic density matrix rho and some factorable informationally complete POVM. Let me restrict, please, to the case of qubits just for simplicity. So now we have an n qubit system, and now I look at each qubit, and I look at an informationally complete POVM. So this can be, for instance, the symmetric, the tetrahedron, or the POVM consisting of the eigenstates of the Pauli eigenstates, essentially, right? So this is informationally complete, and so the measurement probability distribution of that measurement of those measurements on that state contains only information of the state. And now what I do is I take the tensor product. I construct a so you see that A is a vector, but by this I mean this is the element A of M, where M is a tensor product of single qubit informationally complete POVMs, right? So if you want to, A is a string that has as many entries as n number of qubits, and each entry can take 4 values, for instance, if you have an informationally complete POVM with 4 outcomes, okay? And so if you do that, so I will move to this tensor network graphical representation. This will be this will be useful. So this is this guy. No, it's like a tensor with a single index, which is a vector index. I mean, so you see that this is the POVM index A. So I'm representing this guy by this object. Okay, and then I'm representing this POVM M by this object here. So as I said, it's factorable. It's a tensor product of single qubit POVM. So that's why I simply have like local things here. And then this indices here, the diagonal indices here, refer to the POVM index A. And then we have these physical indices, the same indices that act on the Hilbert space on which on which rho acts. Okay, and so of course, if I want to reconstruct the state, this is a linear inversion problem. And then if you solve for that, you get this expression, which is a contraction between P and M, which are both, so I mean, there's this A prime and A, and here there's this 2 index tensor T to the -1, which is the inverse of this overlap matrix. So it's simply the overlap between the different elements of the POVM. This is totally standard. I mean, I didn't do anything. But of course, if you follow this rule, so we have to contract the index of P with one of the indices of T to the -1 and the index of A with the other index, and then this simply boils down to making this contraction here, right? So we get the type of figure that we had in the beginning. So far I haven't said anything about neural networks. This is a totally general probability distribution, totally general state. Any state, if you have an informationally complete POVM, then any state can be written like that. And I think there were complaints. Mateus was complaining. I think he didn't believe that you could represent a generic state like this. But anyway, this is totally general. And yeah, okay. So the thing is that, I mean, the one key feature of this form of writing states is that you somehow swap all the state complexity and all the entanglement into the measurement probability distribution, right? So I mean, of course, these are all local tensor contractions. So I mean, this is so trivial. So all the entanglement and complexity and everything is hidden inside the measurement distribution, right? And this is going to be the crucial thing for these ansatz. And so here comes the ansatz. So what we do is like, say, okay, idea, instead of considering just generic measurement outcome probability distributions, we restrict to objects, to tensors that, or to probability distributions that are obtained by some probabilistic neural network model. Okay, so this is the answer. Okay, so it's a very simple idea. We essentially do the same thing that people did at the level of pure states. We're doing it at the level of measurement probability distributions. And so the result in state parametrization, if you want to write down the state again, now we have states that look like this. I mean, I'm just writing down this contraction here, and you see that if I put the sum over a over one of the indices explicitly, then so now this guy is simply one of the 8th prime arrow of t to the minus 1. And so this is simply the expectation. So this is the expectation value of this object with respect to the model probability distribution. And of course, this can be approximated by Monte Carlo sampling. I mean, so you see that you can write the state. You can approximate the state by sampling from this probability distribution and averaging over this object. Okay, and this is going to be important. And so some features is that I mean, P rho is learned by, so the idea, as I said, so now you have an experiment, you go to the experiment and you make these informationally complete measurements and you get strings. And you input those strings into a neural network and you ask the neural network to try to find a probability distribution that generates those samples, right? That's what it does, okay? And so that's what we call learning, right? And then once it learned that probability distribution, it can sample from that probability distribution, right? So that's the whole thing. This may not always succeed. I mean, there are probability distributions that are the more complex the probability distribution, the longer it will take to learn in general. And as I said, in general, sampling, even if you have already specified the parameters, sampling from the probability distribution is a computational task that can be hard, right? So I'm not, you know, I don't have any. This is more like a dirty, practical approach, if you want to. But motivated, if you want to, with the hope that this has worked very well for many situations in that machine learning people have looked at already. However, oh, sorry. Yeah, please. Sorry. Well, you give all the strings together, right? So you go to the lab, you measure always the same fixed informationally complete POVM, and say that you measure a number of samples, right? N. And now what you have is n strings of outputs, right? And then you go to your and you choose. No. Actually, the strings. So what I input is, if you want, is a vector of length n times the number of qubits of outputs, right? And so what the neural network does is try to maximize it tries to find the parameters that maximize the probability. So there is an ansatz. So you have a probability. You can calculate the probability with respect to the parameters. And so what you do is you maximize the probability of having obtained this n strings of outcomes over the parameters of your neural network. And this is essentially a maximum likelihood estimation. You see? Yep. Let me get there. Yeah. Okay. And so okay. So I was here, and yeah. So as I said, one nice thing is that in many cases we can estimate expectation values of local observables with this technique. And then, of course, I should say there is a problem of course, you know, like I said. So this is a linear inversion problem. So if we have the perfect probability distribution, we invert it and we get a perfect state. But in practice, we will not have, you know, we just have a finite number of samples. So I mean, the matrix reconstructed here in general will not be a well-defined positive semi-definite matrix, which is a bad thing. However, by definition, we simply try to mimic the probability distribution. And so the probability distribution that we have is a well-defined probability distribution. Like I said, so we can calculate many things, many expectation values of local observables, simply sampling from the reconstructed probability distribution. So we don't actually use the density matrix for that. So at least, so this is a bad feature, and this is one of the things that I think that one would like to solve for if one wants to apply these ansatz to other problems. But for the tomographic reconstruction problem, this is not so bad. Sorry? No, I'm not talking about locality here. So this is an important point, and this is perhaps the main departure from MPS tomography. This guy, I mean, so of course we have a polynomial number of parameters describing the neural network, but like you saw, that's why I showed this. Yeah. Uh-huh. Yeah. Ah, yeah. Yes, indeed, indeed. Yeah, yeah, yeah. This we can do, and of course this can give you some estimates of the entanglement entropy, for instance. But but this is tricky because I mean the estimate is good only if the state is pure. No, so we fall into. But I mean. So let me show you. Let me show you. Yeah. So so how do we do it? So I mean, imagine that you have. So imagine that you have an observable O, general observable now. So this is a Hamiltonian matrix, okay? And now so since the POVMs that we consider are informationally complete, you can of course expand this observable as a linear superposition of the elements of these POVMs. And let me call these coefficients a characteristic function, or we'll give it some name, whatever you want. No? And so, of course, the expectation value of this observable with respect to the state can be written like this. I mean, this follows straightly from the answers. I mean, in the end, so if you are able to write down this characteristic function efficiently, and if you are able to sample from this probability distribution, then you Monte Carlo estimate the expectation value of this O, right? Without ever having written the state, but of course, I have to have a good estimate of this probability distribution. I have to be able to make this index contraction with a characteristic function efficiently, and I have to be able to sample from the reconstructed distribution, right? And so, okay, so this word classical is wrong, forget it. I mean, it's just the average over this distribution, right? And so, what we do, so of course, in many cases, we're interested simply in calculating the expectation value of a single point correlator or a 2-point correlator or something, some k-body correlator that does not depend on the total number of particles. And then in that case, we can do that quite efficiently. I mean, given that I was able to reconstruct the probability distribution, right? And I have to, I'm still owing, I still need to show what's my figure of merit for the reconstruction. But let me, for the moment, assume that I was able to reconstruct the probability distribution. So then, so it's, you know, it's this simple, this trivial contraction here, and this we, like I said, this we estimate by simply sampling outcome strings from the reconstructed probability distribution and taking the average of this object, which is, as you can see, is trivial to construct, no, because it's a tensor product of local things, right? So given if so the main message, the take-home message would be if I am able to sample, the rest is all efficient tensor contractions. No, so as I said, so you have a probability, so you have a neural network that has some parameters for a model for a probability distribution, right? Once the neural network has found the optimal parameters that it has, then that's it. Then you simply press a button and you obtain outcomes. Press a button and you obtain outcomes. Press a button, it's a black box. No. No, it gives you the samples. It gives you. I mean, you can calculate. I mean, you have the parametrization, so in principle, you can calculate the probability distribution. However, this may be difficult, but that's not what you do. You know, you store the parameters, the parameter values there, and you simply, if you want to, you can think a la black box, and you press a button, and you get the outcomes. It's all approximation. Also, the learning process involves sampling. So it's all the time, all these things are done by sort of what they call it, this Gibbs Monte Carlo. Well, I mean, yeah, it's Monte Carlo Markov chain, essentially. I mean, but yeah, so what you have is a tool for sampling. And so this sampling is used for both learning And while you're learning, you kind of you know this gradient descent thing. So you sample with different values. So you move away until you are happy, and then once you stop, you say, okay, from now on, I will just fix these parameter values and press the button and get a sample. Yeah. And so as a nice example, for instance, something that one could calculate is the overlap between the reconstructed density matrix and an MPS. Right, so this blue thing should be understood as a fixed bond dimension MPS, which is contracted with the physical indices of my state ansatz. And of course, this is algorithmically efficient. I mean, it's all, as I said, it's all efficient contractions. But what we have observed is that in practice, the variance of this guy may depend on the number of particles. So I mean, this is a bad thing. I mean, we're not able to give, for instance, nice estimate of the fidelity of the reconstruction with respect to a target MPS. Suppose you want to prepare an MPS, right? Well, but I come to that. I will come to that. I'm just, but I have, like, what we will do. We will have like an approximate estimate of the fidelity, but it's not so nice as the quantum fidelity with respect to an MPS state. But this is my next slide. Anyway, but for this case, all the observations that we have done are very efficient. I will show you later the experimental results. Okay, so as the certificate, and here this is what we use as the benchmarking, and this is, if you want to, the dirtiest part of the work. So what we consider is actually the classical fidelity between the let's say the experimentally observed measurement distribution and the reconstructed one, right? Or if you want to, if you know the state that you want to prepare in the scenario of certification, right? So yeah, you could compare the classical fidelity of your model reconstructed probability distribution and the ideal one that you would expect. Okay, and now I'll come to the advantages and disadvantages of this. And then, but let me for the moment just define it. I mean, it's you all know it. This is a classical fidelity between two probability distributions. I can multiply. So say that rho tilde is my reconstruction by my neural network, and rho is either some known target state or some experimental state, depending on which scenario you're interested. Well, whether learning or certifying a known, the preparation of a known target state. And so I divide by this P of rho, and I get this expression here. And so, of course, now I can write this as the expectation value with respect to P of rho of this random variable. And now I can, again, estimate it by sampling from the, so by using the, let's say, for free, I have measured on this, this is like the experimental distribution, so I sample from it. This I get for free. And so if I can now have an estimate of this guy, then I can have an estimate of this. Is it clear? So in the case of certification, where you're interested in a known target state, you can even have a formula for this guy. This is your reconstruction. This you have, and this you have a formula. In the case where you're simply learning, then this is a bit worse, because here you have to input the histogram columns that you observe, right? But it's still an estimate. And so what we have observed, and so of course, this is not nice. I mean, in general, one would like to have a lower bound of the quantum state fidelity. But it happens that these classical fidelities give you an upper bound. And so, but the heuristic behind the choice of figure of merit for benchmarking is that since you're looking at informationally complete POVMs, somehow you expect that, you know, I mean, if both probability distributions are equal, well, since the POVM is informationally complete, this can only happen because the states themselves are equal, right? And so one expects, and this is heuristic again, one expects that the larger or the closer the value of the classical fidelity is to 1, at some point the quantum fidelity should catch up, but we don't have a lower bound. Okay, so that's why I say that it's an approximate certificate, but at least we don't make assumptions on the and so you can even test that Like you can actually, so this is a very simple example with a 2-qubit belt state under depolarization. And so we have always observed that when the classical fidelity raises, the quantum fidelity also raises. Of course, at a much smaller value, but we so far we have not observed a single example where when the classical fidelity goes up, the quantum fidelity doesn't go up. And so, of course, this is not a proof. This is dirty, but again, this is the price we pay for having something versatile. And I think that this is the so the main motivation is that we're considering informationally complete POVMs. No? So all the information is contained in the probability distributions, and then you simply look at how similar the probability distributions are. So you can do this with a classical fidelity, but you can also do it with a relative entropy or any other measure. I see. Mm-hmm. Mm-hmm. Yeah. Yeah. No, sure. No, I mean, the worst case, it's definitely bad. No, I mean, so I think that I think that this idea has potential usefulness as a first check of many body state preparations, and once you have, I mean, you can use it as a sort of raw, let's say, estimate, and then you can, as a sort of to guide you if you're going in the right direction or not, right? But this is never going to give you a lower bound to the, or, I mean, we don't see it how to get a lower bound to the quantum fidelity actually. Yeah. Between the two fidelities, you mean? Yeah, I don't know what's the rule for the. Mm. Mm. Yeah. 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 No, I agree. I agree. I mean, this is the this is, I think this is the price we pay. I mean, right. No, no, no. Yeah. Yeah. No, but this, but then no, but I don't think we'll be able to do that because, like I said, I mean, so here this is all. I mean, this trick is all with respect to the same information, like complete POEM. I don't know how you would get around that, but perhaps I'm not understanding what you're saying. Um, mm. Yeah, we don't. Right, that's the thing. We wanna avoid that. Yeah. Mm. Mm. Yeah, but this basis change is what they were doing in this other paper, where they were assuming pure states, and I could, yeah. But then I think I will always have to compare the same informationally complete. I don't think that you can write the classical fidelity, or that it makes sense. Right. I mean, if I take the measurement probability distribution with respect to one measurement, and I see the fidelity with respect to a measurement probability in another measurement, then this does not have the heuristic motivation that I want here, that when both distributions are equal, then this can only happen only when the state is equal, right? So this is a feature that I would like to preserve. Yeah. And so anyway, so I'm not hiding it, right? I mean, I think that this is a bad feature, and I think that this is something that we still that we may still improve or look at, right? I mean, this is still work in progress, right? But let me show you the preliminary results that we have for the state reconstruction, right? For the numerical experiments, and it's just a couple of lights, and I'm done. And so what we do is we use this as the figure of merit of our reconstruction. We ask to have, I don't know, a classical fidelity of 0.99 or 0.999 or such things. And when we have that, we stop. And as I said, this is not, yeah, well, we know what we have, yeah. And so the numerical experiments that Juan has run, so there are three figures that I'm going to show. One is the one in which you learn. So what we do essentially. So here we consider the antiferromagnetic translationally invariant transverse field Ising model, and we look at the ground state, right? And so what we do is so what he does is he uses the MRG to generate an approximation of the state. Now he applies the measurements on that state and generates samples from those measurements on that state. And this is just for the training. I mean, this is the part that you will do in the real lab, right? And so once you get those samples, you feed them into the neural network, and this is our contribution, so to say, right? So this is just to generate synthetic data on these things. And so we have looked at both POVMs, the tetrahedron or the Pauli eigenstates, and you can see that that it reproduces very well not only the single point of correlators, but also the two-body correlators, right? And so this is something that they were not able to do with the previous model. So we were happy to see this, and this is a one-dimensional lattice. So the next thing that I suggested to him, hey, is it possible that we try to do this for a two-dimensional lattice? And then he did it. So again, here the most expensive part of these experiments is to generate the synthetic data. The training of the neural network is really fast compared to generating the synthetic data. So here, for instance, we have an 8x8 spin lattice, and again, so it's a triangular lattice. It's the Heisenberg, the nearest neighbor Heisenberg model, and as you can see, like it reproduces at least at first sight the two-body correlators very well, right? And this is and one nice thing that he liked about it is that like you can have a complicated sign structure of the wave function. That was not accessible with our previous technique. And so, of course, this simply tells you that the neural network is indeed able to learn the state. But of course, we want to know something about the sample complexity. I mean, how much statistics, how many samples do I need to acquire as the number of qubits in order for the reconstruction to be good? And the thing is that for this task, we have to go to simpler states, because generating the synthetic data is so expensive that if you want to generate it for, say, 1 qubit, 2 qubit, up to 80, then it's really painful, right? So then what we do for that, so we consider the simple state, the simple case of locally depolarized GAZ states up to 80 qubits, and then what we do. So here is a plot of, let's say that. So on this axis is like the classical fidelity, and on this axis is the number of samples that I need in order for my reconstruction to have a classical fidelity of 0.95 or any value that you want. And so what we observe is that in this simple case, the sample complexity is approximately linear, right? So I mean, this is a first indication. This is a first indication of a nice thing, but of course, it's really a shame, or it's a pity that we cannot analyze the sample complexity of more complex systems because of this difficulty of building the synthetic data, right? But as I said, I'm quite happy with these results. I think that like everything in machine learning, it's dirty, but I think it can give experimentalists a first indication of whether they're doing well or not in a regime that I don't think it's so easy to attain in reconstructions with other techniques. At least not always. No. Of course, you know, here I'm thinking of the fact that this ansatz is by definition non-local, so it's expected that at least it may perform well on cases where MPS tomography may not. But again, this is just heuristics and numerics, right? And so with this, I want to conclude. So I talked about this reliable neural network state tomography, and the simple trick here is just to propose the neural network ansatz at the level of the measurement statistics. And as I said, the main thing here is versatility and practicality here. And it's a sort of combination between machine learning techniques with tensor networks and, of course, Monte Carlo sampling. It can deal with mixed states, and it can accommodate any neural network probabilistic model. And if you once you have a reconstruction, then it has this nice feature that it allows you to calculate expectation values, estimate expectation values of some observables. And of course, it may fail, but if successful, you have this approximate certificate of the classical fidelity between the two probability distributions. And so, as outlook, I mean, I think that apart from the tomographic problem, I think that this may be an interesting state parameterization to look at. I don't know. I don't have any. Of course, we have this problem of we need some practical way of imposing positive semi-definite, and we don't want to do it at the level of the density matrix, because otherwise then we're back at the density matrix representation, and we know we can do it with, up to small dimensions, right? But of course, one could simply use supervised learning to somehow teach the machine to learn to recognize positive versus non-positive states, just in terms of the probability distributions. This may be some idea. We haven't tested at all. But it would be nice to have some semi-analytic constraint that one could impose somehow at the level of the structure of the neural network itself, or at the level of the measurement probabilities, right? Of course, if one could do that, then one could use these ansatz for state optimization, say, or such things. Of course, but here I'm being a bit too optimistic, if you want to, just to provoke you, right? And so with this, I'm done. So this is Juan, this is Giacomo, this is Roger, and these are the collaborators involved in this project. And of course, I cannot show external collaborations without showing the people with whom I work the most in Rio. Well, actually, so I'm non-locally split between Rio and Sao Paulo. So this is Leo, who's a postdoc in Sao Paulo. Carolina is going to defend master thesis next month. There's Renato, who's a PhD student. For those who were here last week, now he looks more like this. And here's Ranieri, who should be somewhere there. And he will talk on Friday about a totally unrelated problem. And Marcio was here, and Eric, they were also here. And there may be new postdoc positions. There may be a postdoc position shared between Perimeter Institute and Sao Paulo, and it's probably there's an opening in December, and even there may be 2 more postdoc positions in Rio, which is kind of a miracle nowadays in Brazil. So. yeah, indeed, yeah, true. Yeah. Okay, so that's it. Thank you for your attention.